this particular model is of a piece of just a section of one skeletal muscle cell. That's it. So just a piece of one skeletal muscle cell. Here's the endomysium connective tissue wrapping around the outside of the cell. Here's the sarcolemma, the actual cell membrane under the endomysium, seeing exposed there. This would be an axon terminal of a single somatic efferent neuron. So inside the axon terminal, we see all these little Golgi vesicles, all these little yellow Golgi vesicles. Acetylcholine molecules will be packed inside here for the release into the synaptic cleft. So a gap right there with what's called the motor end plate portion of the sarcolemma. So this is sarcolemma, and all of this is sarcolemma. But this indented and folded region, rippled region, the sarcolemma is specifically called the motor end plate. So when an action potential travels by saltatory conduction along the axon of our somatic efferent neuron, reaches the axon terminal, opening up voltage-gated calcium channels, calcium enters, causing the exocytosis of these vesicles, releasing acetylcholine into the synaptic cleft here. All these little dots you see on the rippled sarcolemma, the motor end plate sarcolemma, they would be nicotinic cholinergic receptors. And we know about nicotinic cholinergic receptors. They are chemically gated or ligand gated sodium ion channels. So acetylcholine would bind, gates would open, net movement of sodium in by facilitated diffusion, and we would get a depolarizing local potential called the end plate potential. This is the motor end plate, so we get a depolarizing local potential called the end plate potential that spreads to the surrounding sarcolemma, which does not have nicotinic receptors, but does have voltage-gated ion channels. So we get depolarization threshold, bang, action potential traveling along the rest of the sarcolemma in both directions away from the motor end plate right here. Oh, by the way, I discovered, this was news to me, I discovered just last week why they've got a nucleus showing there. This is a little sidebar, this is not test material. I just wanted to share what actually a Schwann cell, this is a Schwann cell surrounding the axon terminal. I didn't know they did that. I just discovered last week. This is accurate, that there really are Schwann cells around each axon terminal. They don't myelinate. The axon terminals are gray matter, they're not myelinated, but every axon terminal has a Schwann cell wrapped around it. So I didn't know that. But now you know. Now you just learned what I learned. All right. So definitely skeletal muscle. We see the shallow nucleus here, just under the sarcolemma. And interior view, we see these log-like, cylinder-like myofibrils. So this is a piece of one skeletal myofiber, a cell. Myofibril, 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 which will take off for the moment. Come back to that. Okay. So this longitudinal view, I'll just make it a cross-sectional view. You can see 1, 2, 3, 4, 5 myofibrils within this one skeletal myofiber. In between the myofibrils are many mitochondria, here in red, and you can see the blue-gray sarcoplasmic reticulum also intervening between them. So longitudinal view, sarcoplasmic reticulum, mitochondria. Let's see. Let's do the longitudinal view. So we have this one myofibril here in the center, and coming in from the sarcolemma, T-tubule or transverse tubule. There's another one coming in. There's another one coming in. There's another one coming in. Look where they are. Every transverse tubule is an inward continuation of the sarcolemma. Look exactly where they come in. They come in right along the border between an I band and an A band. Between an I band and an A band. Right there. So I band has the thin myofilaments, the A band has the thick myofilaments. So right where I band and A band meet. Where this is an I band, and this is an A band. There's another I band. I band, A band, I band, start another A band. So there's the border between I band and A band. There's another I A border. Transverse two do indeed come right along the border between I and A. That is accurate. All right. What else? The Z-disc. This is one Z-disc, one large protein sheet holding all these myofibrils within the cell together, and the Z-disc forms the center of a whole group of I bands. There's another Z-disc, broad protein sheet forming the center of another whole group of I bands right there. So that Z-disc is holding all of those I bands together throughout at this point in the cell, throughout the entire cell. Okay, extending from each side of the Z-disc are thin myofilaments, small in diameter, as we learned today, composed of actin, troponin, and tropomyosin. Let's see what else. So take a look at one myofibril from one Z-disc to the next Z-disc. This portion of myofibril is called a sarcomere. Sarcomere is a piece of one myofibril from one Z-disc to the next Z-disc, right there. So the myofibril can be thought of in two different ways. As a series of sarcomeres, sarcomere, 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 etc., or as a series of I band, A band, I band, A band, I band, A band. Either one is fine. Either one is correct. There's two different ways of looking at the consecutive structure of the myofibril. Let's see. The A band, here's an A band, has an M-line, very, very small protein sheet just holding that one A band together. And that M-line protein sheet also holds a bundle of thick myofilaments, these orange bands, holds together a bundle of thick myofilaments. That's the A band. The A band's width is from one end to the other end of the thick myofilaments, from there to there, from there to there, to there, so on. And we can see, extending the Z-disc with these thin myofilaments partially overlapping, thin and thick, thin and thick. Here in the center of the A band, just thick myofilaments. Let's see, so what do we call that central region of an A band? It's just thick myofilaments. That's the H zone. It's the H zone region in here. So this higher A band, this thick myofilament central region, is the H zone. What's the center stripe of the H zone? It's the center stripe of the A band as well, the M. All right, let's see. And this part that I took off shows a sarcomere, Z-disc to Z-disc. So this is the Z-disc to Z-disc portion of one myofibril. So from there to there is one sarcomere. Here we have a series of thick myofilaments, there, etc. So they're bundled together to make one A band, one complete A band. So the A band is the central structure of the sarcomere. What's holding the A band together? That M-line small protein sheet. The H zone is right there, just thick, just thick, just thick. So this is the H zone. Z-disc extending from the Z-disc, a series of thin myofilaments, right there. See partial overlap, and so we would have a distinct H zone when the sarcomere is in its relaxed state. Have a definite, fairly broad H zone when the sarcomere is not contracting. So this is the relaxed state. During contraction, the thick filaments link to the thin filaments. Thick links to thin, thick links to thin. And then, remember those heads that are angled outward? When they link, what do? They bend inward. What's that going to do? Going to pull these thin filaments toward the center of the sarcomere, like this. Pull them in toward the center. So here we see, look how far apart the Z-discs are, and In a relaxed sarcomere, look how much closer the Z discs are in a contracted sarcomere. The thin filaments are pulled in toward the M line. What's wrong with this is this should allow the thin filaments to come all the way in. They should actually come into contact with the M line. So then it doesn't go in quite far enough. Is that sort of thing you wanted me to go over?